Hey everyone, welcome to another video by Simplilearn. In this video, probability density function, we will tell you everything that you need to know about the probability density function and how to implement it, both in Python and in real life. So, let's get started. So what can you expect from this video? What's in it for you? First, we will go over the basic definition of the probability density function, followed by the steps to find the probability density function. There are three main steps, which is summarizing the density using histograms, parametric density estimation, and non-parametric density estimation. And finally, we will see how to implement all three of these steps in Python. So now, let's dive into the definition of the probability distribution function. What is probability distribution function? A function which defines the relationship between a random variable and its probability such that you can find the probability of the variable using the function is called a probability density function. In simple words, probability density is the relationship between an observation and their probability. Some outcomes of a random variable will have low probability density and other outcomes will have a very high probability density. Basically, the probability of a variable x happening or occurring will vary, and it can sometimes take on a lower value or it can take on a way higher value. The overall shape of the probability density is referred to as probability distribution, and the calculation of probabilities for specific outcomes of a random variable is performed by a probability density function, or PDF for short. Now consider a variable x with a PDF of f of x. This is what your probability density function will look like. There might be a point where the probability of x occurring is very high. Hence, your probability distribution function, or f of x, will also be very high. At other points, the distribution or the probability of x happening or occurring is going to be very low. Hence, your f of x is also going to have a very small value. Basically, given the random sample of a variable, we might want to know things like the shape of the probability distribution. This here is something called a normal distribution, where your probability distribution function takes on a bell shape. However, this is not the probability density function that might always occur. There are different probability distribution functions and all of their graphs look very different from each other. Knowing the probability distribution for a random variable can help you calculate movements of the distribution like the mean and variance, but it can also be useful for other more general considerations like determining whether an observation is unlikely or very unlikely and might be an outlier or an anomaly. Like, consider this graph itself. In this graph, these points over here, which have very less probability distribution, are outliers, which means that the chance of them occurring is very low. And basically, this is not something that you're going to see in your regular scenario for your variable x. Now let's consider 2 points a and b, which are values that our variable x can take. P of A and P of B just represent the probability of A and the probability of B, which can be found out by drawing a straight line and coinciding it with our graphs. The area under the graph over here, which is going to give you your probability of this region occurring, can be written as probability of A less than equal to X, which is the probability that we're searching for here, less than equal to probability of B. What does this mean exactly? This means that this area is always going to be greater than or equal to the probability of A, but less than or equal to the probability of B. This gives us the narrow region of the probability which is present over here. And doing this, we can find the probability of occurrence for any value of x. Suppose you want to find the probability of B happening. For a probability distribution function, the probability of B happening is not simply this point here, but the entire area of the graph which is taking place before this point itself. So if you want to find the probability between these regions, you're going to have to find the entire area and not simply the probability at one point. Now, so far we've been talking about different types of variables, which is discrete random variables and continuous variables. What exactly do these mean? A variable which can only take a value within a certain range is called a discrete random variable. The value is usually within a certain distance of another finite value. An example of this would be the sum of two dices. Basically, values which are well defined are called discrete values, and a variable which has well defined values will be called a discrete random variable. This variable can only take values which fall within a certain set of values. Let's say you roll a dice. The dice can only give you specific outcomes which range from 1 to 6. This is what you would call a discrete output. On the other hand, a continuous random variable can take on infinite different values within a range of values. For example, the height of a student. The height of a student is not fixed. Even if the height is 1.7 meters, in reality, the height can be 1.77 or 1.765 or 1.789. The exact height is very hard to determine because it's not easy for us to find the precise value of the height of a student. So basically, the height can take on an infinite different range of values. When we're trying to define the values that a continuous random variable can take, we usually say it in the form of a range of values, which means that the value can fall in that range and can take on any value in that range. It's not like a discrete random variable where you can define definitive values. Now let's understand a probability density function with the help of a graph. Consider the graph below, which shows the rainfall distribution in an year in a city. The x-axis has the rainfall in inches, or the amount of rain that we're getting, and the y-axis has the probability density function of getting that amount of rain. The probability of some amount of rainfall is obtained by finding the area of the curve to the left of it. So let's say we have a point 3. If we want to find the probability of 3 inches of rainfall occurring, we would have to find the area of the curve which falls to the left of 3. When we draw a line from 3 which intercepts the graph and further extend it onto the y-axis, we get a value of 0.5. Simply put, this means that the probability of 3 inches of rainfall occurring is going to be lesser than or equal to 0.5. The exact probability can be found out by finding the area of the curve, which falls to the left of 3. How do we find the probability distribution function? The first step is to summarize your density with the help of a histogram. The first step in a density estimation is to create a histogram of the observations in the random sample. Now, what is a histogram? A histogram is a plot which involves first grouping the observation into bins and counting the number of events that fall in each bin. The counts or frequency of observation in each bins are then plotted as a bar graph with the bins on the x-axis and the frequency on the y-axis. The choice of the number of bins is important as it controls the coarseness of the distribution and in turn how well the density of the observation is plotted. It is a good idea to experiment with different bin sizes for a given data sample to get multiple perspectives or views on the same data. At the same time, the number of bins is important as it determines how many bars the histogram will have and their widths. This will change not only the shape of the graph, but also how the graph is read. This will also determine how a density is plotted. Now, let's see how we can summarize our density with histograms using Python. First, let's import all of our necessary modules which we're going to require. We're going to require matplotlib to plot graphs. We're going to need the normal random function so that we can get a normal distribution. We're going to import mean and standard deviation from NumPy to use on our graphs. And also going to normalize our data. So we're going to import the norm function from SciPy. We finished importing all of our necessary modules. Now let's generate a sample which has a size of 1000, and it's going to be a normal distribution. And we're going to also plot this with the help of a histogram in bins of 10. So as you can see here, you get a normal distribution, which is nothing but a almost bell-shaped curve. And we have 10 bins here, which are centered at 0 and which extend from -3 to 3. How will our graph look if we change the number of bins though? Let's run it and see. So you still have a normal distribution, but it's not as well defined. Because of how less the number of bins are, you lose a majority of the data which will contribute to your normal distribution. It doesn't look like a proper normal distribution, but it looks more like a discrete data at this point. Now let's take a look at the next step of finding our probability distribution function. The next step is called parametric density estimation. What exactly is parametric density estimation? The probability density function is of many types. The shape of your histogram will help you determine what type of a function it is. We can also calculate the parameters associated with the function to get our density. Now, different probability distribution functions will have different graphs which will have different shapes and which will also have different parameters like mean, standard deviation, etc. associated with them. Using these parameters, we can find important points of our data. Hence, it's very important for us to recognize what type of a distribution it is. Common distributions will occur again and again in different and sometimes unexpected domains. Getting familiar with common probability distributions will help you identify a distribution from a histogram, and once identified, you can attempt to estimate the density of the random variable with a chosen probability distribution. This can be achieved by estimating the parameters of the distribution from a random sample of data. Now, an example of this would be a normal distribution which has two main parameters, the mean and standard deviation. Given these two parameters, we will now know the probability distribution function. These parameters can be estimated from data by calculating the sample mean and sample standard deviation. This entire process is known as parametric density estimation, and it includes identifying your probability distribution function and getting the parameters which are associated with it. Now, once we have estimated the density, we can check if it's a good fit. This can be done in three different ways. One is plotting the density of the function and comparing the shape to the histogram. The next is sampling the density function and comparing the generated sample to the real sample. And the last one is using a statistical test to confirm if the data fits the distribution. Now over here, as you can see, all we've done is taken our data and plotted the density function on top of our histogram, and we've compared the shape. So the density function that we're actually considering here is a normal distribution. And from this graph, we can see that it's almost an exact fit to our histogram. Now let's see how we can perform parametric density estimation using Python. To begin with, let's generate a random sample of 1000 observations from a normal distribution with a mean of 50, which is determined by the LOC parameter, and a standard deviation of 5, which is determined by the scale parameter. Now, just to show you what the distribution looks like, we're going to plot it in the form of a histogram. So this is what the histogram looks like. But this is just to give you a basic idea of our data and what it looks like once plotted. But let's assume that we don't know the probability distribution and we don't know what it looks like as a histogram, and we don't know that it's normal. So now if we just assume that it's normal, we can calculate the parameters of the distribution, specifically the mean and the standard deviation. We would not expect the mean and standard deviation to be 50 and 5 exactly, given the small sample size and the noise in the sampling data. So because of this noise and the small sample size, we have a mean of almost 50 and a standard deviation of a little more than 5. Now let's define the distribution as normal. So now using this, we've defined a normal distribution. We've used the norm method of the SciPy library, and we're doing this with the mean and the standard deviation that we've obtained from our samples. So up until now, we're just assuming that it's a normal distribution, and because of that, the parameters that we've calculated is the mean and standard deviation. And using the calculated mean and standard deviation, we've gotten a normal distribution. And up until now, again, keep in mind, we do not know for certain that it is a normal distribution. So far, all we have is this data. So the next thing that we're going to do is fit the distribution with these parameters and then sample the probabilities for a distribution for a range of values in our domain, which in this case is 30 and 70. So all we're doing is we're calculating probabilities for a range of outcomes, and in this case we've taken 30 and 70 as our domain. So these are the probability distribution values for the normal distribution that we've defined over here, and this is basically gonna give you the outline of your normal distribution. These are the points at which your normal distribution will be plotted. Now what we're basically going to do is we're going to plot our histograms using the samples that we've already generated along with the values and probabilities of the normal function that we defined over here. So as you can see, it's almost a complete fit. The normal distribution that we have here is made using the mean and the standard deviation of our actual samples. The reason we took mean and standard deviation was because we assumed it was a normal distribution, and the parameters associated with the normal distribution are mean and standard deviation. Using the mean and standard deviation, we got the normal distribution. We calculated probabilities for this normal distribution using a random domain of 30 and 70. And we plotted the probabilities and the values on top of our histogram to see if the normal distribution was a fit to our histogram. If it was not a fit, you would have to go and do the same procedure with other common probability density functions until you found a function which was a proper fit to your histogram. Now let's move on to the final step, which is used in the calculation of our PDF. This final step is called non-parametric density estimation, and it's only used when the shape of a histogram doesn't match a common probability density function, or it cannot be made to fit one. In this case, we will calculate the density using all samples in our data using certain algorithms. This is only done when a data sample does not resemble a common probability distribution, or it cannot be easily made to fit the distribution. And this is often the case when the data has two peaks. This is also called a bimodal distribution, or it has many peaks, which is also called a multimodal distribution. In this case, the parametric density estimation will not be feasible, and alternative methods can be used that do not use a common distribution. Instead, you will use an algorithm which is used to approximate the probability distribution of the data without a predefined distribution, which is also referred to as a non-parametric method because we're not using any predefined parameters. The distribution will still have parameters, but these are not controllable in the same way as a simple probability distribution. For example, a non-parametric method might estimate the density using all observations in a random sample, in effect making all observations in the sample parameters. Now consider this graph which has two peaks. This is not a normal distribution or any other sort of distribution that we are familiar with. So for this, we're not going to use a parametric estimation method, but we're just going to calculate the parameters for every single sample point in this. Perhaps the most common non-parametric approach for estimating the probability density function of a continuous random variable is called kernel smoothing or kernel density estimation, or KDE for short. Kernel density estimation is a non-parametric method for using a dataset to estimate probabilities for new points. It uses a mathematical function and smoothing probabilities, so the sum of the resultant probabilities is always 1. Now in this case, a kernel is a mathematical function that returns a probability for a given value of a random variable. The kernel effectively smooths or interpolates the probabilities across a range of outcomes for a random variable such that the sum of probabilities always equals 1, a requirement of well-behaved probabilities. You also have a parameter called the smoothing parameter, which controls the scope or the window of observations from the data samples that contributes to estimating the probability for a given sample. As such, the kernel density estimation is sometimes referred to as your Pearson-Rosenblatt window. Now, at the end, you also have a basis function, which is a function which is chosen to control the contribution of samples in the data set towards estimating the probability of a new point. This is only done to make sure that you're not learning from a lot of noise and that you're not using a lot of the outliers. Again, let's see how we can perform non-parametric density estimation with the help of Python. So first we'll start by importing all the necessary modules along with the kernel density estimation, which can be imported from sklearn. Now let's create a bimodule distribution by combining two different samples, sample 1 and sample 2. Sample 1 has 300 examples with a mean of 20 and a standard deviation of 5, while sample 2 has 700 examples with a mean of 40 and a standard deviation of 5. We're then going to use hstack to merge both of them together to get a final sample. The means that we've chosen, which is 20 and 40, are chosen close together to ensure that the distributions overlap in the combined sample. So this is what our distribution is. Let's just plot it so you get a basic idea of what our graph looks like. So this is what our graph looks like. Now we already know that none of the various different probability distribution functions fit these graphs. So now we're going to perform non-parametric estimations. So to perform non-parametric estimations, we're going to use the scikit-learn machine learning library, which provides the kernel density class that implements kernel density estimation. First, the class is constructed with the desired bandwidth or window size of 2. And your basis function, which in this case is a Gaussian function. It's a good idea to at least test different configurations to your data. And in this case, we're only going to try a bandwidth of 2 and a Gaussian kernel. But usually there are multiple different kernels that you can, that you can play around with. And you can also tweak your bandwidth to exactly fit the distribution that you have. Now let's run this. So now we've gotten our kernel density estimation. Now we can evaluate how well the density estimates matches our data by calculating probabilities for a range of observations and comparing shapes to the histogram, just like we did for the parametric case before. So again, we're gonna just calculate different probabilities using the kernel density function. And we're just gonna plot it on top of a histogram to see how well the kernel density function is estimating for our data. So these are the probabilities that we've gotten finally with the kernel density estimation. And now we're going to plot it on top of our histograms. So as you can see, it's almost a complete fit. It's just left out some of these outlier values, which again are ranging very high. But overall, we have a pretty good fit. The only problem is it's not very smooth, and you can again try tweaking the bandwidth to different values. So let's just in this case try tweaking it to 3 and see how well it runs. Okay, so now we've gotten new probabilities and let's run it on top of our bandwidth. So again, we using a bandwidth of 3, you can see that we're fitting our data even better, and we're again ignoring a lot of the outliers which are out there. So this is going to give us a better estimation. And with that, we come to the end of this video on probability distribution function. We hope you enjoyed this video. If you did, a thumbs up would be really appreciated. Also, here's your reminder to subscribe to our channel and click on the bell icon for more on the latest technologies and trends. Thank you for watching and stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.